Okay, so introduction to probability. Here's the basic concepts. What is probability? Uh, just right out of the book, there's two things. There's a few things that are involved. Uh, we call probability an experiment. So if I'm rolling dice, that's called an experiment. I've got a dice. A dice has how many sides? 6. Has the numbers. A typical one has one. Well, a typical dice has 6. There's many different types of dice, right? Especially if you play Dungeons and Dragons or some other things, you got 12-sided dice. But we're going to talk about a 6-sided dice, a cube, and it's got the numbers 1 through 6 on it. Okay, um, so that might be an experiment. I roll the dice and see how many times I get a 2. That's called a probability experiment. So what I do is in each experiment, I have outcomes, and the outcome is what I roll. Okay, that's what happens. So there's an outcome. The event is any particular outcome or group of outcomes. Okay, this is we'll explain this in a little bit better. A simple event is an event that cannot be broken down further, and a sample space is a set of all possible outcomes. What does that all mean? So let's see if we can put that all together with the example of rolling a die. Okay, so I'm going to roll a die, and I count how many times I get say, a 2. Well, let's just roll it once. Okay. Let's do this. Let's make it a little bit more interesting. So all the possible things that could happen when I roll a dice, I can get a 1, 2, 3, 4, 5, 6, right? Those are all the possible. Are those simple outcomes? Well, yes, because that's as simple as could be broke down. Now, if I was rolling 2 dice, I could get it more complicated. I could keep track of, I could have a red dice and a green dice, and I could keep track of what, 2 different numbers, so that gets more complicated. I could also keep track of the sum, which we will be doing by the end of the day. But when I just got one dice or die that I'm rolling, it's either it's 1 through 6, and it's pretty simple. That's all that can happen. So I go and I keep track how many times I roll it and I get various values. Then I get another 2, and I get maybe a couple 5s, and then I get another 2. So I rolled it that many times. Okay, let's say that's my data. Roll, and I mark down whether I get a 1, 2, 3, 4, 5. So how many total times did I roll this die? Looks like 9 times. Count 9. I think I got 9. This is the hard part. So this is a cool part. The main skill you need for probability is you need to know how to count. And it sounds weird, but that's what my probability. I took graduate level probability, and that's what he says. Probability is just counting. Of course, by the end when we're done, it's going to be more complicated counting of larger events, and then you use some funky formulas. We'll get to that in chapter 9. A little touch on it. We won't get too bad, but for this, it's simple. Yeah, there were 9 experiments. And so that's the total number of things that happened. It's 9 options, not 9 possibilities of getting a 2. The event that I was looking for, though, is what? I was looking at my event because I wanted to see how many times I got a 2. Okay, so my event is a 2. It's any particular outcome. That's what I'm looking for. It is a simple event because that's all that could happen. It's not complicated. We'll look at cards. They get a little complicated. I could talk about a queen. I can talk about a queen of hearts. So sometimes that's what we talk about not being a simple event. But this, all I can say is I either got a 2 or I didn't get a 2, right? Pretty simple. The sample space, this is what the sample space looks like. It's all the possible outcomes. I've kind of recorded it. And then for a probability, what I do is I count how many of my events did I get and divide it by how many total experiments I did. So how many times did I get a 2? There's counting again, right? 3. How many times did I do my experiment? 9. So for this particular experiment, my probability of getting a 2, 3 over 9, which can reduce to 1/3, which you'll see I turn to a decimal, 1 divided by 3, with a bunch of 3's going on forever. I multiply this by 100 to turn it to a percentage, and I'd get 33.3%. Those are 3 different ways of representing a probability. As a reduced fraction, that's a correct answer. And in some of the book, that's what they want you to put. They want the reduced fraction. And in Math AS, if they ask for the reduced fraction and you give it the decimal, it'll mark it wrong. But sometimes it'll ask for both. Sometimes they want it as a decimal. So this would be your answer. Sometimes they ask for it as a percentage. This would be our answer. So notice we just multiply by 100. Okay. And again, if you watch those videos, I do several problems where I just do the counting. I get the fraction. I reduce the fraction. I turn it to a decimal. I turn it to a percent. So you get all the 3 types of answers for a probability. Okay. So far, so good. That's probability. We're done. No, almost. What I like to break it down to is what a probability is, and they'll write it this way: probability of some event A happening. So it wouldn't be math if we didn't have a lot of letters that mean nothing, right? That's math for you. But don't worry too much. We'll call it event A, getting a 2. Okay. I like to just simplify it. It's the good things. I'll use the pound symbol because in my day we use that to represent the word number. So the number of good things divided by the number of total things. And I use that word good in a very open sense. I don't know that it's good to roll a 2, but that's what we're wanting to happen. Okay, that's what we're looking for. So whatever we're looking for, we count how many times that happened, and we divide by the total number of things that happened. And that's a probability every time. Count, and divide. That's probability. That's it. And for this lesson 8, chapter 8, that's all we're going to do. Okay, and we'll look at some other examples and see how that works. The thing is then we're going to now have to look at some of the things that happen with this, some principles that come out of this. Okay, so far so good. So don't worry too much about translating sample space and event or this and a simple event. It just gets some of these words and these definitions kind of get my mind out of whack. But if I can think of good things over total things, I'm just counting, and that's all that's going to go. That's all that's going to happen. So sometimes in this PowerPoint, we have some pictures. In the book, they have some pictures. Like with cards, it's really, sometimes it's good when you're doing a card problem to actually look at a deck of cards and just count how many are in that particular thing they're talking about. How many red cards are there? Out of a deck of 52, you can see that half of them aren't, so it's 26 red cards. But sometimes if you haven't been playing with cards a lot, you might not know that. And it's just like, where are people getting this? Well, they've had experience with cards or something, or just look at a picture of a deck of cards and then do the counting. That's where all this stuff comes from. Okay, let's go here. And let's move forward, I think. Click on that. Oops, that button. So this is what they say. Again, I break it down to good things over total things. They just got a lot wordier, right? A probability of an event E, could have used A, but some event is the number of outcomes corresponding to the event E, quote, number of good things, divided by the total number of equally likely outcomes of what happened, okay? And again, probability is a theory. And it works on of this concept of something called equally likely. What does equally likely mean? Good. And so on a die, is it possible that they're not equally likely? What's that? All six of them, yeah. Is there a way to make a dice not equally likely? Anybody cheated in playing the dice game before or heard of it? Loaded dice? You heard of loaded dice? You weight one side so it's more likely to come up a certain number. That's not equally likely, and that's called cheating. Uh, but probability is based on most of the time we think if there's six things that could happen, we make an assumption that they're equally likely, but we might be wrong. Okay, like even flipping a coin, if you look at it, especially those who are in chaos theory, usually one side of the coin's a little bit heavier. I think like one because it's got the face, it's got a little bit more metal on that side. Does that maybe make it slightly more likely to land with face down than face up? Okay, those are the types of things that we do with experiments because we make an assumption that it's equally likely, but we might be wrong. Okay, and so with dice we can load them, and then it's no longer. And if you get caught, that is illegal. They'll take you to jail. Okay, but what I want you to do is a lot of times in probability for convenience, we say things are equally likely, like it's equally likely to have a girl as it is to have a boy when you have a child. But if you look at the numbers, it seems like there's slightly more females born than males in some, you know, and it's like 50 point something more females. So, but we make an assumption, okay, and we'll talk about those, and that's kind of what we're working on. We might be wrong. This is all theory. So here's expressing probabilities. Notice one way to do it is as a fraction. We can also do it as a decimal. But what ends up happening, can you ever have more twos than trials? Can you ever have more of something happen than what you tried to have happen? If I only rolled 9 times, could I get 10 twos? Well, no, because I only rolled 9. So the most I could get, I could have rolled all twos. And so the biggest number I could have got, 9 out of 9. Okay. 9 out of 9 gives us what? That gives us 1. That's the most we could do. If I didn't roll any twos, 0 out of 9, what does that give me? 0. Good. So from 0 to 1 is all the possibilities that could have happened. And this definitely is in there. Okay. So all your probabilities, if I say I've got a 200% chance of happening, what am I doing? I'm lying, or I'm gilding the lily, or I'm overemphasizing, but you can't have a 200% chance. You can have a 100% chance. You can have 1 is the biggest probability you can get. You can't have more than 100% probability of happening. Okay. Otherwise, you're talking something else. You also can't have a negative probability of happening. You can have 0, means it won't happen. And we'll see this next slide kind of does it. Probability 0 means impossible. Probability 1 means certain. It will happen. So if we go outside and it's raining, we say the probability of rain is 100% because it's happening, right? We're okay with that. So we get this kind of a scale going on from 0, impossible, to 1 is certain, and everything in between. 50-50, we say that's kind of a, equally likely, equally unlikely. Less likely below 0.5, more likely above 0.5. That's how we go about life. Okay. So far, so good? Okay. So probabilities will be between 0 and 1, which also means 0 and 100%. Which means the top of the fraction will always be bigger than the bottom of the fraction, or equal to, right? That's how it's going to work. So again, here's some math, some inequality notation. The probabilities will be 0, equal to 0 or bigger, up to being equal to 1 or smaller. So a number between 0 and 1. Now, this is where we get into a situation where we have to be a little bit more careful. And this is developing the sample space. It's not quite obvious that we have to count it in a particular way, but let's take a look at this. Okay, let me take this down. So let's just ask this question. Assuming, and again, remember that word assuming, doesn't mean it's true, it's just we're going to think that it's true, that we have an equal chance of having a boy or a girl at birth. What's the probability of having 2 girls and 2 boys in a family of 4 children? So just on the surface, 2 girls, 2 boys, and out of, we've got a family of 4. What would you feel, what's your gut instinct saying would be the probability for that to happen? 50-50 seems reasonable. 4 children, half are girls, half are boys. That seemed like 50-50 because there's a 50-50 chance. But let's get to our counting. How many different types of families can you have with 4 children? Okay. Well, would you agree you could have
4 girls, 4 boys?
Good, good. Let's keep. It's weird doing this thing because I sometimes not sure what screen I'm on. There we go. Okay. So I could have 4 girls. Girl, 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 girl. Or I could have all boys. Boy, 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 boy. Or I could have what?
3 girls.
I could have 3 girls, 1 boy, but that was girl, girl, girl. Could I have 1 boy and then 3 girls? Is this a different family than this?
No.
Anybody have? I had 4 boys and 1 girl, and the girl was the oldest. That is a different family if the girl would have been the youngest. I guarantee you. My older sister bossed us. She was our boss, and we listened to her because she was older. And had she been the younger sister, what would she have gotten? She would have got 4 bully boys telling her what to do, right? But it really is a different family. It's weird because the question doesn't say anything about birth order, but the physical outcome is the girl in this case, the boy happened last, the boy happened first. It really is different. Um, and not only that, the boy could have happened here. So we could have had a girl, a boy, a girl, a girl. We could have had a girl, a boy, and a girl. And this is where and then we've already counted for the girl, girl, boy. So there's actually 1, 2, 3, 4. There's 4 different ways to have a family with 3 girls and 1 boy. And I'll get back to the slide because it's already done this. But this is the complicated part. I tried to make it sound like probability was just like this simple thing. You just count and good over bad and you're done. But the counting part is where it gets complicated because we got to count all the physical things that could happen. And while the problem didn't say birth order is important, it actually is. It's a different family. And even though we're not counting the age of the children, it happened differently. Now, if they're all, if you had quintuplets, even quintuplets, they usually come out one at a time. I don't know if you do a C-section, get them all, but usually even with twins, one was born first, one was born second. In fact, there was one, I thought, was it this year that they had twins and one was born right on New Year's Eve and the other was born in the next year. You saw that on the news? That's kind of cool. They're born basically a year apart, or they have 2 different years of birth for twins. And interesting. Okay, so now back to the slide. And again, the PowerPoint will show you all the different ways, and it makes it a little easier. These are all the different ways, and we just kind of focused on 3 girls and 1 boy, and we saw that there was 4 different ways to do it. And now looking 2 girls and 2 boys, it's not just one way of happening. There's 6 ways to get 2 girls and 2 boys. How many total ways of getting a family of 4 children? 16. I count 16. Anyone else? That's good. And we'll click a button, it'll show us at 16. So there's 16 ways to have a family of 4. I'll just do it this way. Click it. And there's 6 ways of getting 2 girls and 2 boys. So our probability is going to be what? 6 divided by 16. 6 over 16, which if you divide it with a calculator is 37.5%, or 0.375 multiplied by 100, 37.5%. Not quite the 50-50 we would have thought at first blush. So this is where probability gets to be, it gets the complication. And again, if you were betting on the things, as the thing is this is reality. And if you were to actually go and find a bunch of families that had 4 children, if you got enough of them, say 1 million of them, you'd find about 37, probably you would find 37.5 of them had 2 girls and 2 boys. And you go, wait, I thought there should be about 50%. But again, if you actually go measure it, you'll get pretty much close to these type of numbers. And this is important because, again, a lot of this probability, so there's people who love gambling. There's people who think gambling is this evil. And there's people that are in between. A lot of probability, for gambling, it's really probability of events. So that's the mathematics that probability oftentimes gets used for. But there's other applications of it as well. Insurance. It's all based, the reason you pay whatever you pay for your car insurance is all based on probability. They're trying to measure your probability, your personal probability of getting in an accident. So they look at your age, your gender, your marital status, they look at your credit history, because they do all the numbers and they're counting and they're trying to see what is your probability of getting an accident. And if you are in a group that has a higher probability, you will pay a higher premium because you're more likely to file a claim, so you have to pay for your share of it. If you're in a group that has a lower probability, you will pay a lower premium. That's why we don't all pay the same amount for car insurance or health insurance or whatever. So health insurance is a little different, but that's where this is another strong area of probability is insurance. Okay, so far so good. So counting, but counting's not always easy. That's the hard part. Okay, the thing on top of it is there's really 3 different types of probability. So far, we've been talking about theoretical probability, equally likely events and such, but there's 2 other kinds. One's experimental probability, and experimental is simply that we actually measure it. We count. That was my dice game that I gave to you at the beginning. That was experimental probability. But there's also subjective probability. That's one of my favorites to talk about. And when I was learning it, they never talked about it, but it's really something that we all use. It's our own, and we're never wrong because it's our opinion. Okay, so theoretical probability, we roll a dice. The chance of rolling a 4, since there's 1 4 out of 6 different numbers, 1 out of 6, right? 1 divided by 6. That's the theoretical probability. And again, this is directly from the book. It's just what we were talking about, number of good things divided by number of total things. That's theoretical probability. So we just count, this dice has how many 4s on it? 1. How many could we roll? 6, 1 out of 6. Okay, so that's theoretical. That's what we've been talking about. Probability of rolling a 4, there's our dice. Count the number of 4s. There's 1. Total outcomes, how many different things could happen? 1 through 6. There's 6. Make the ratio 1 divided by 6, 0.67 or 16.7% for rolling a 4. And again, it gets more complicated. Usually there's no dice game, but just rolling a single dice. It's rolling 2 dice because then it makes the probabilities more interesting, I guess. Okay. If we roll a 6-sided die, calculate the probability of rolling an odd number. Okay, so let's do this together. Rolling an odd number. How many odd numbers are on a 6-sided die? 3. 1, 3, and 5. Yeah? Let's see what happens if I click here. Here's our die. That's what it looks like. Count the number of odds. There's 3 of them, right? So that's 1, 3, and 5. The problem is sometimes we get confused because the number 3, there is a 3 on the dice, but then there's a count of 3, right? So those are 2 different things. Total number of outcomes, we could get a 1, 2, 3, 4, 5, 6. So there's 6 outcomes. Our ratio is going to be 3 over 6. which reduces down to 1 over 2, which is a decimal 0.5, which is a 50%. Okay, that's probability. And again, when we deal with the simple ones, that's how most of the problems will start, with the simple stuff, and then we start counting, getting to more complicated counting. But again, the actual calculation of a probability is just number of good things divided by number of total things. So far, so good? Okay, so you guys help me with the pacing, because sometimes I go too slow, sometimes I go too fast. So equally likely outcomes. At some random moment, you look at your clock and note the minutes reading. So you're looking at your clock, you're just looking at the reading of the minutes. What's the problem? And the reason I do this, I think there's a problem like this in the homework. What is the probability the minutes reading is exactly 15? Again, not taking count of the hours. What would you think that would be?
1 out of 60.
Good, because there's 60 minutes in an hour, right? So there's 60 different things it could be. There's only 115. Let's see, there's a watch. So I show you, because again, you have to see it. There's 6, and I chose a special watch to see that there is a total of 60. Count the amount of 15s. Well, there's 115, although you can't see it because they've got the date thing there, but there would be a 15 there. There's 1. Total of outcomes, you could count them, but you could see there's 60, starting with 1 minute all the way to 60 minutes. And so make the ratio 1 out of 60. So it's just 1.67%. Very, 1 out of 60. That's the probability. Awesome. Awesome. What's the probability of the minutes reading is 15 or less?
1 out of 15. 15 out of 60.
Good. Let's start with the easy counting, and you might be right on the other ends. The number of that actually, this is where it was. Yeah, this got me wrong. The first time I thought 15, but if you count 15 or less, now less than 15, you got to go 1, 2, 3, 4, 5, 6, 7. Oh, I know what the problem is. The 0 minute. Yeah, because I spent about a half hour on this. Because I came up with 15 as well, and I was going, where are they getting it? And I had to go do some research, and I said, oh yeah, 60 is also 0. So you picked it up right away. So you have to count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And you get to 15, you get actually that there's 16. And the only reason I did this, I knew this because I tried this problem, and the back of the book said 16. I go, come on, I'm a math teacher, I should know this. Oh shoot, I forgot to count the 0 minute. So, and that's why I put this face there. Is if you actually see things, then you make it as concrete as you can by looking at pictures. But there's still 60 total outcomes. Make the ratio 16 out of 60. 4/15ths, which is 0.267, which is about 26% chance. Okay, so far so good.
Yeah.
So again, physically look at some things, but that's nice. That's what I like about Math AS. When it tells you you'll do something and tells you you're wrong. Sometimes, like on this one, I would just push through 3 times until it gave me the right answer. Then I go, wait, 16. Where's it getting the 16? Where did it get? And actually, wouldn't give me 16. It might give me 4 out of 15. So I have to kind of backtrack. But you can work backwards from the answer sometime and figure out what it's doing. And then after about 5 minutes of thinking it, that's when the idea that 60 must also be 0. Because you start at 0 minutes. It took me a while. Okay, so you're sharp. Okay, here's another example. Again, I put this in because there is some examples using Venn diagrams. So this is just sort of a basic of how to use a Venn diagram to count. And basically, we won't go into great details. We will when we get to lesson 7. But if it's inside the circle, then that is telling you it's got that quality. So this circle here that it says women, how many women are there? 7 plus 5. Because these 5 are women. They're also in the parent circle, so they're women who are parents. So how can you differentiate between these 7 women and these 5 women? We call them different things. We call these 5 what? Mothers. Right? Because they are parents. They have children. So these are women who have parents. Oh wait, these are women who are parents. Means they have they're mothers. These 7 women don't have children, so we don't call them a mother yet, but they're just women. Okay, so see how that goes. These 6 parents, what do we know about these 6 parents? They are men because they're not women. Okay, that's actually, we know they're not women because they're outside that circle, so then we jump to the conclusion that they must be men. These 2 here, they're men that don't have any children, right? Because they're not in either of the circle. Okay, so that's how it is. So that helps us with the counting. So when we go to 1, what is the probability of randomly meeting a person in this room who is a parent? Well, okay, so how many people are in this room? We have to add all these together, right? Let me just 12 and 8, 20. So there's 20 people in this room. Let me click. Oops, no, I didn't write anything down. So I'm going to switch over to the screen for those watching the video. Let's come back here. So we'll do this. So there are 20 total people in the room. How many of them are parents? 6 plus 5. Okay, so those 5 in the middle are women parents or mothers. The 6 are male parents or fathers. And so together there are 11 parents in that room. Okay, so just when you're using the Venn diagram, sometimes just got to be careful about the counting. And that's what we'll focus on this one. We'll use Venn diagrams for counting. And when we get to lesson 7, we'll use it for other things. So that's our probability there. What is the probability of randomly meeting a person in this room who is a father? How many? Back up a little bit. You reduced too quickly for me. So fathers, there's 6 out of 20, right? Which you reduce down to 3. Wait, there's 6 parents, there's 6 male parents out of 20, which will then be 3/10. Good. Because each of these can be divided by 2, and that's how we reduce. And we could leave it as that. We could also turn it to a decimal, 0.3 or 30%. Okay, good. And again, a lot of you are probably faster at math than I am. I am not a fast guy at math, but I'll get there. Okay, we'll get there. So far, so good. Okay. Let's go back here, click here. Here's another one. Again, just showing you that we're counting, but now we get a little bit more complicated way of counting because we're going to use this table that has broken up, looks like some sort of a political event, men and women, Republican, Democrats, and independents, how many of each in the room or at the meeting. And then now what is the probability that you meet a Democrat? Okay, so how many people are in the room?
150.
All right, yeah, it's a big room, huh? So 150 is going to be our basis. So we do this as probability as a Democrat. How many Democrats are in the room? 6. So it's total, both men and women. 64. So we can see that right here. And that gives us the fraction 64 out of 150, which again can reduce. This is one of the reasons when I do probabilities, I like to think of them in percentages. So I don't have to reduce fractions each time. I just take 64 divided by 50. I get a decimal, and I can turn that to a percentage by moving the decimal over 2 places. Does anyone have a calculator out?
32 over 75.
32 over 75. And then what is it as a decimal?
0.42666667.
Okay, a lot of 6s. And so I could round this to, 42.7%. Okay. And to me, it's easier. If out of 100 people, there's 42.7% chance of it happening. Okay, all right, So come and work with the percentages. What is the probability that you meet a male Republican?
21, 150.
Okay. So male Republican, there's only 21, but again, we're still out of a total of 150. Of course, now if we're over in the Republican side of the, because you know Republicans and Democrats probably aren't going to mix too well. They'll be in a certain section, right? Um, but maybe they're all mixed. So equally, that's the, see, this is the assumption. It's equally likely. But if you're on the Republican side of the room, you have a better chance of meeting a Republican than if you're on the Democrat side of the room. So, uh, but we just do that. Okay, so men would be, yeah, 21 out of 150, turn it to a thing. What is the probability that you meet someone who is, okay, this is an important one, someone who is not a female Democrat? Not a female Democrat. So how could we count this?
You'd subtract 40 from 150.
Very good. We look for how many female Democrats there are, which is 40, and then we subtract it from the total. Rather than try to count all the other stuff and try to add it, just find what we have and subtract it from the total. Okay, so to answer that question, probability of a female Democrat, we're going to say 150 minus 40 out of 150. Okay, that gives us 110 out of 150, and we can reduce that, get the zeros off, that's 11 out of 15, or as a percentage,
0.73333. Oh, so 73.3.
73.3%. Very good. Again, if you practice this, just reducing the fraction, doing the decimal, doing a proper percentage, you're actually also just going to, when you get to 4, it's just going to be boom, piece of cake. Okay? Make sure, I always got to make sure I wasn't in front of everything. Okay? Is that kind of making sense now? Okay. It's like if it has a 40% chance of rain today, what's the chance of it not raining? 60%. So again, we get that complement of things. If it happens or not happening. And the probability both of either not or it is always 100%, because that's, you know, does or it doesn't. Very good. Go back here. Let's see, experimental probability. I'm going to be a little bit slower today because I did an introduction, but I want to take you through a few of these. Here's an experimental probability. It's done a lot in sports. They have somebody who keeps statistics on how many times you shoot a basket and how many times you make the basket, how many times you get to bat, how many times you know, get on base or something. There's all these statistics. That's all experimental probability. And just as in basketball, you count, okay, how many times did the player make a free throw? How many times did she attempt it? So if this particular player, she made 23 out of 25 attempts, just make the ratio, which is 23 over 25, ends up being 0.92, which is 92%. So she's a 92% free throw shooter, simply because of the facts. Now, on maybe a day where she's a little sick, it's not as good, but again, this is just taking the numbers and doing it. Okay, counting. How many times did she make it? How many times did she try? That's going to kind of determine. Again, we do this in sports, but then there's days when, you know, our favorite player is not doing as good. Maybe they're a little sick. Maybe they're injured. So those things change. And that's the thing with probability. It's just kind of a guess. It's oftentimes just measuring what happened in the past. But if you watch my videos, I think I've got one with, how many of you guys know, I forgot his name now, motivational speaker, Anthony Robbins? You do? Yeah, I went to one of his events. He just pumps you up with all this positivity and stuff. But there, in one of my videos, you have to watch it. I think it's problem number 14. I can't remember. I did a little, it does this probability thing. It says the past does not determine the future. So I always try to throw some positive stuff in there. So, you know, now you start watching all these videos to find the little Anthony Robbins guy. But yeah, I think he's great. Okay, so that's a experimental probability, and that's what a lot of research is about. They do the research and they count, and they say, now this, you know, if I do this, I've got a 60% probability of increasing your performance in school, and if I teach you this way, I have a certain percentage of this and that. So again, it's just a matter of, that's what all research is about. We We try something, we count. Okay, probability, another application. This is my favorite. I think I got the video coming up, and hopefully you'll be able to hear it. But if not, it's a short one, so I can explain it. Subjective probability is an educated guess. Okay. A gut feeling. And just thinking of a gut feeling, I saw a show that was talking that actually, did you know in your stomach you have as many neurons as a cat or dog has in their brain? I never knew this until last semester I found that out. You in your gut, you actually have neurons. Neurons we think of as being up here in the brain, but we have a second brain down here. In fact, that was the name of the show. I think it's called The Second Brain. And they actually say that maybe our stomach was our first brain and this thing developed later. And that's why we're always, we're centered around food because this is what the brain was for. It was looking for good food, right? And that made a bigger brain to go find some better food or something. But when you talk about a gut feeling, you have neurons down here. And if you put all those neurons together, it would be the size of a small cat or dog brain. And cats and dogs are pretty smart critters, aren't they? I think they are. Uh, they can do some, and so your gut feeling. I want you to start thinking that your mental capacities are not just all up in your head; they're also throughout your body. Okay, so the probability someone will go on a date with you. Okay, now I think that if the video works, how many of you seen the movie Dumb or Dumber? Okay, so you already know the scene we're going to go to, right? He's going to, as a Lloyd, he's asking out the girl if she'd go out with him. So let me just go. I think this is all. Uh, oh shoot, why is it not speakers? I'll. Well, you'll have access to this, so if you want to see it. Basically, remember, what is he saying? So he says, "What's the chances of you going out with me?" Right, something like that. What does she say? Like 1 in a million. And what is she, so she's trying to tell him what? No, no way, guy. I'm trying to let you down easy, 1 in a million. But what does he say? So he's saying there's a chance. So in his mind, in her mind, it's 0%. In his mind, it's like almost a sure thing. I got this sexy body. It's going to happen. There's a chance it's going to happen. So this is subjective probabilities that go on. But this does have some sound, but this is the problem. There's a chance. Yeah, okay, there we go. So we see it. He is just excited. So this is subjective probability, and we do it all the time. And again, people throw things at us to try to tell us, no, it's not going to happen. But we don't let it get to us. We say, there's a chance. What's your chance of getting into this? Well, 1 in a million. There's a chance. I'm going to do it. And oftentimes it's those people who were told 1 in a million, they were the 1 in a million. We are the 1 in a million. Okay, we keep going. We don't take no for an answer, right? Because if you take no to an answer, you've given into it. You're not going to have that chance because you don't try anymore. If you ignore it and say, yeah, there's that. That's what I love about this. I mean, it's kind of funny stuff, but more of us should be like the Lloyd and Dumb and Dumber. We should be dumber than we are smarter. Because when we're dumb, we just say, there's a chance. Let's make it happen. And if you watch the movie, they got together, didn't they?
Yep.
I don't know if it was a real thing or she was like an FBI agent or something. I can't remember. It's been a while. But in real life, they actually got together. They were married, weren't they? I think the two actors were married. Or maybe they were just dating. Uh, more research for you to do. You can figure it out. Okay? So anyway, this is what I love about math class is we get into subjective probabilities even. You're waiting for your friend at the coffee shop. Depending upon which friend it is, you might say they're 5 minutes late. You'll say they're not showing. If it's 5 minutes late, you said, oh, maybe something's happened. Or if it's 5 minutes late, you say, well, another 10 minutes they'll be here. And that's your subjective probability, somewhat based upon experimental, reality that you've experienced. But you've got your subjective feelings for those. Okay, and they'll change over time. Okay. Complement of event, we've already actually talked about this. The complement is the probability it doesn't happen. So it's just simple. But what I do is I show you that in mathematics, things can seem very complicated. But it's really just, this little bar over the top is really the probability of the event not happening. That's all that bar means is not. This means it's going to happen. So if you take 1, which is 100%, subtract the probability it does happen, you have the probability it doesn't happen. Yeah, that's just rain. It rains 40%. It's got a 40% chance of rain. 60% chance of not raining. Okay, that's all this is saying. And it works both ways. The probability of something happening, if I know what it probably is, if I told you it was a 60% chance of not raining, you could tell me what that means, a 60% chance of rain. Sorry, 40% chance. Do the math right, right? Okay, so that's all this is mathese, but it's a simple concept. Complements, right? To complete to 100. Probability happening, probability not happening. Chance of rain is 40, chance of it doesn't rain, 60. So 100 minus 40, we can get it either way. Okay. And the thing is in some probability class, this makes our calculations a lot easier. Like when we were doing the female Democrat, it was easier to just take the number of female Democrats, subtract from the total, rather than going around and counting all the people who were not female Democrats and then adding them all together. That's a lot of work. So a lot of times, if you can see a question is phrased in this way, you can save yourself some work. Okay. I always did all the work and then figured it out later, but hopefully you'll be there. So 40 plus 60 is 100%, or 0.4 plus 0.6. Okay. This is kind of, I think, our last concept for today is odds. Odds is different than probability, but it's measuring the same thing. And what I want to give you as an example, I when I was growing up in Portland, Oregon, they had dog racing. They had horse racing too, but horse racing, I think you had to be 21. Dog racing, you only had to be 18. So I could start going to the dog races when I was 18. And I was hanging out with people that did that sort of stuff. And anyway, I was reading. I thought I was right out of high school. I was good with math, I thought. And so I'm looking at the racing form and I'm trying to calculate. I thought I could use math and just really come away really good. The problem is I didn't know it at the time, but race forms are based on odds. And I was calculating probabilities based on the odds. And so everything I was doing was out of whack. And I'm going to show you how that works. Odds is kind of the same thing. Again, it's measuring the same thing as probability, but it's using it in a different concept. It does not use the total. So I'm going to take this down. So this is a formal application. It's the probability of event over the probability of the event not happening. So you could think of it as probabilities, but I like to relate it back to counting. Let me see. I can't remember what's in the next. So chance of rain is 40%. Chance of it not raining is 100 minus 40, which is 60. And so what we get is we get a ratio of thinking of it maybe 40 days it'll rain and 60 days it won't rain, the number of ways it can rain, the number of ways it can't rain. We get this odds is 40 to 60. Okay. We can reduce that to 2 to 3, or we sometimes write it as a fraction as well, but we don't want to turn it into a percent. Odds should not be turned into percents because then we start thinking of it as a probability. This is not a 66% chance of rain, right? It's a 40% chance of rain. But if we were to report it as odds, we'd say it's 2 to 3. 2 times it'll rain, 3 times it won't rain. So a 5-day period, we could expect 2 days of rain, 3 days of no rain. That's what that means. It's what we've broken it down with odds. But that is not a 66% chance of rain. That's a 40% chance of rain. So see how there's this disconnect in how these two numbers, whether we think in probabilities or whether we think in odds. Most sports betting is based on odds. So if you're a sports bettor, you're going to be good at odds. Craps, a lot of casino type games are based on odds. So you got to think in odds, not in probabilities. And it's a little difficult to go back and forth between the two because they are different. You see, probabilities are good to total. Odds is good to bad. It's what we get with what we don't want. It's wins to losses. Again, so a lot of sports stuff is reported with odds, not with probabilities. And again, even my young startup in math, I thought I knew what I was doing, but I didn't. Okay, so these two are different. So watch, if you're in Math AS and you're getting it wrong and you think it's right, look closely. You might see the word odds there instead of probability. or some of the problems it has both, it has to calculate both. But just remember, they're calculated differently. They're both a matter of just counting. So we're counting, but with odds, it's how many ways something can happen, how many ways it doesn't happen. We don't ever use the total. Odds against is really the same calculation, but we just take the reciprocal, okay? So how many ways it doesn't happen divided by the total ways it does. Now this, with odds, we can easily get a number that's over 100% if we were to turn it to a percentage. So chance of rain is 40, chance of not rain is 100 minus 40, which gives us 60. And then you do the calculation. This is 60 to 40. This is the chance of not raining, or the odds of not raining. We could use the word chance in both cases, but it's odds, it's not probability. And we can reduce this to 6 to 4 or 3 to 2. Okay, so that's and oftentimes in gambling, they call this odds against. There's odds on and odds off, or odds on and odds against. So you got to be careful about what they're talking about because they throw these things at you. And sometimes they're trying to confuse you. So math can be used in a way that is confusing because there's multiple ways to talk about things. And again, if you're not really experienced in using things, sometimes the more experienced will try to pull the wool over your eyes. Okay, but again, the goal of this class is just that you are aware of all these things. And when you become aware of things, you'll see that gambling is, while you may win sometimes, in the long run, we'll do this in chapter 9. We'll do some calculations of expected values. All gambling games are set up so that the house will, in the long run, will win. So the more you gamble, even though you may win once in a while, you might have a big win. If you continue gambling, the universe is in the favor of you eventually losing, and eventually the casino. That's why there's casinos keep popping up. Some of us go in a little bit, play, have some fun. That's fine. But when we will all eventually be losers if we keep playing, but just play long enough. Okay. Again, there's some people that do it. They make a living off of it. Maybe card counting, whatever. They find a system that works for them. That's great. But most of us, the more we go, the more we go. So here, I just show you that here's a picture of a deck of cards. 52 cards is this. There's two suits that are red, the diamonds and the hearts. There's two sets that are black, the clubs and the spades. And they have things called face cards, which are the ones that have a picture on it. So that's a jack, queen, and king are what's considered face cards. So some of the questions might ask you about that. But when you go to answer the questions, if you need to take a look at this, there's also this picture is in the textbook as well. So you'll be just counting cards, and again, it's just good over total. If we're doing probabilities or odds, it's number of ways something can happen compared to what number of ways it can't happen. Okay. Oh. This one the video works. The sounds kind of, yeah. So this is, your neighbor tells you that he heard on the radio that the probability of an earthquake of magnitude 7 or higher hitting California in the next 10 years is 1.2. How do you know that this is incorrect? It's over 1. Okay. So that's, again, maybe he heard it on the news, maybe someone said it's got a 120% chance of happening. It's absolutely going to happen, but if you say it's a 100% chance, that's certainly going to happen. But 1.2 is yielding a little, you're putting too much on there. But I thought, oh, there's an earthquake, and these guys just coming out of a building. Fortunately, they weren't in that building, right? Or near the building, standing next to the building. But this, and I don't know. I'm not saying that was in California. It's just I searched the internet for a little picture because I figure the more you can make these things concrete, the better. Okay. Your favorite basketball player is an 84% free thrower. Find the probability he does not make his next free throw. 84% chance he's going to make it. What's the chance he's not going to make it? 16%. Good. So it's just a subtraction. I think I do the work here. There's our player. Make it or not make it. 84% he's going to make it. Not going to make it. 100 minus 84. 16%. Okay, simple as that, or as complicated as that, but that's it. You either make it or you don't make it. You can't half make it. Right? You hit the rim, that's kind of good. You got close. It either makes it. You don't get 2 points for getting close. You got to get in. Okay. Or you can work with the decimals. Again, I always find my personal preference is to work with percentages because it's the decimals just scare me for some reason, and I get them off or something. But you can work with decimals, so it's the same thing as 1 minus 0.4, 0.84, or 100 minus 84. You'll see in most of my examples, when I work with numbers like this, I'll work with the percentages because I can think in terms of 100 minus 84 a lot easier than I can think of 1 minus 0.84. I got to go to the calculator for that one. But I could get the 16% in my head most days. Here's another example, just a few examples to try. So I've gone through the few tries. Board game has a spinner that's divided in 8 different colored sections. The sections are red, orange, yellow, green, blue, blah, blah. Find the odds the spinner landing on a primary color. Primary is red, yellow, or blue. And we're going to assume that they're all the same size. So I'm going to click here. Here's my spinner. So what's the odds of being on a red, yellow, or blue?
3.
Good. So there are 3 in the primary colors. There's a total of 8 colors that were mentioned. 3:8. It's not a. We don't make it a decimal. It's not a. This is not a probability. This is an odds. Number of primary colors are 3. Total number of. Oh wait. There's 8 different colors. This is odds. This would be good for probability, right? Sorry. What's the number of non-primary colors? There's 5. Good thing I have this outline for me to follow through. So there's 5 that are not primary. So when we deal with odds, it's number 4 and number against. So make the odds 3 to 5. Okay, 3 to 5, 3 to 5, or 3 over 5. But don't make it into a percentage or a decimal because that makes it a probability. Okay, so that's tricks you. Okay, we'll be doing both. Just make sure you follow through on those. Find the odds for drawing a club from a standard 52 deck. So again, the word odds, right? So how many clubs are there in a deck of cards? 13, actually. There's 13 in each suit. Count the number of clubs.
Oh, okay.
There's 13 of them. And then count the number that are not clubs. So out of 52, 52 minus 13 is 30. Let me click the button. 39. So do the subtraction. 52 minus 13. So there's 39 that are not clubs. So when we want odds, we don't want total. We want how many ways to do it, how many ways not to do it. And then we just make a ratio. So it's 13 to 39, and that doesn't reduce. So we write it with a colon. We can write it with the word 2 between it. We can write it as a fraction. I don't like writing them as fraction, but for some reason Math AS likes them as fractions because I like to save the fractions for probability because that tells me to go do that. I'd like to just put them as a ratio with the colon. I know it's an odd. Okay.
Do we always break the ratio down to the reduce?
Yeah, they usually.
So it would be 13 to 39? Or if it was like,
yeah.
Say it was double that or whatever. Do
right.
you always break that down
if it can reduce.
Ratio?
Yes.
So just always reduce everything.
Yeah.
Okay.
And you'll always be correct.
Okay.
Yeah. Make the odds against. Just flip it, right? There's 39 ways for it not to happen, 13 ways for it to happen. So odds against is just the reciprocal.